Good afternoon, everyone. My name is Luis. I'm from the MicroBooNE collaboration, and today I'm going to talk to you about how we have used Pyhf and some key understandable searchers that we have done with the MicroBooNE detector. So, so this is just an outline of what I'm going to cover today. Because this is not an LHC experiment, I will try to give a brief introduction to the MicroBooNE detector and the kind of searches that we are doing with this MicroBooNE detector, and I will try to explain super brief the experimental principle behind the detector, and then I will just go through the two searches that we have performed so far where we use Pyhf. So MicroBooNE is located in the Fermilab campus and is roughly here in the middle, in this blue circle that you can see here, and is a liquid argon time projector chamber, and this is a diagram of the MicroBooNE detector. So you can see this cylinder vessel, which is the cryostat that we use to keep the argon at a low temperature, and inside you can see this parallelogram, which is the TBC itself. That contains the active volume that we actually use to perform measurements. So we had a total active mass of roughly 85 tons, and the size of MicroBooNE is roughly an school bus, American school bus. They asked me to be precise with this and actually practice the talk. And it is located at surface level. This is important because because it is at surface level, we get a lot of cosmic rays crossing the detector. So yeah, moreover, MicroBooNE it was, because now has been decommissioned, was exposed to two neutrino beams. One is the Booster Neutrino Beam that has a proton energy of 8 giga-electron volts and is on axis with respect to the detector. And we also were exposed to the NUMI beam, which has a higher energy, 120 giga-electron volts, and is off axis with respect to the detector. So this is nice because using these two beams, it allows us to perform several measurements spanning from neutrino physics, oscillation measurements, cross sections, large TPC for R&D for future detector experiments such as BooNE, and obviously the scope of this talk, BSM searches. So let me now try to explain you briefly how a large TPC works. So in this detector, we have inside this box some argon at low temperature, that's why it is liquid. And whenever a neutrino comes inside the detector and interacts with an argon nucleus, it produces secondary particles that some of them might be charged. As these charged particles propagate through the argon, they ionize the argon, and they also, the argon excites and releases scintillation light. So these ionized electrons, we capture them using an electric field to drift them toward a readout. We have 3 different readout planes, which are set of wires set in different angles. And we also collect the scintillation line using photomultiplier tubes. So this is really nice because from the readout of MicroBooNE, we can make this really nice event displays from the one that you can see here. So this is our like bubble chamber-like images that allow us to very precisely tell what particles we are seeing here. For instance, in this example that I'm showing here, this is a neutrino interaction, a muon neutrino interaction, where the short track is actually a proton and the longest track is a muon. And in the upper right corner, you can also see one of the cosmic muons that I mentioned before. So this is nice because, as I just mentioned, MicroBooNE is exposed to 2 high intensity neutrino beams. They not only produce neutrinos, obviously, they produce a lot of charge mesons, neutral mesons that are interesting for BSM searches. And the nice features of the MicroBooNE detector itself, it has a really nice calorimetric capacity and good particle identification too. So using this, we can perform several beyond the standard model searches. We have done a few so far. Here you have like a list of some of the models that we have explored, but today I'm just gonna cover 2 of them, which are heavy neutral leptons and light dark matter. So where does Pyhf fit in this story? We want to prove BSM models, and to do that, it involves performing hypothesis tests and using many high energy physics dedicated tools such as the asymptotic approximations and the CLS method. So historically, in MicroBooNE, we have been doing this using RootStats or an even older framework called Kodi. Both of them are C++ packages. The nice thing about Pyhf is that it all offers all these tools, but embedded in Python, which is one of the most used languages nowadays. So now I'm going to tell you a little bit about the two searches that we have performed using Pyhf. I'm going to start with heavy neutron leptons. So heavy neutron leptons are BSM particles, which are right-handed fermion singlets, and they can have masses from kilo electron volts to giga electron volts. And they mix with the standard model neutrinos through the extended PMNS matrix. And because of this, the production and the yield rate of heavy neutral leptons are scaled with the matrix element that you can see here. So in MicroBooNE, we have performed many HNL searches. And today I'm just going to focus on this recent search that we have performed using the Neutrinos Beam, and is just accepted by PRL like last week. So we are showing this like for the first time here. So let me describe the strategy that we use to search for these heavy neutral leptons. Here we have a diagram of the Neutrinos Beam line and the position of the MicroBooNE detector with respect to the Neutrinos Beam line. So basically here we have protons that are coming from the main injector, and they hit the Neutrinos target and they produce a lot of charged mesons. But some of these protons manage to reach the absorber of the beam, where they can also interact. If they interact with the absorber, they may produce, for instance, kaons, which can decay in the absorber into a heavy neutral leptons, and some of these heavy neutral leptons will travel to the MicroBooNE detector. This is nice because they will come from a particular position, and it's really good for background reaction. So that's the concept of this search. HNL can decay through several decay modes, but in this search we are focused in just two. The first decay mode is into a pair of electron-positron pair, which is given by this red branching ratio that you can see here. So basically, this is the mass range that we want to cover with this channel from 0 to 150 mega electron volts. And this is how one of these decays will look like in the detector. You can see we have two electromagnetic showers that are really tiny. They only last for a few centimeters. And they come, here you can see this feature that they come from a very particular position in the detector. The second mode that we looked in this search is decay into a neutrino and a neutral pion, which is given by the blue branching ratio here. And in a similar way, you can see that once the pi naught is produced, it will decay into two photons, and the two electromagnetic showers produced by the two photons will be slightly separated because of the conversion distance of the photons. So here, what we do in a few words, we have as our many high-level features that we are able to reconstruct using the MicroBooNE, using the software that we use in MicroBooNE, which is called Pandora. And we feed many of these reconstructed features into a BDT using SGBoost, which is the state of the art in terms of BDTs. So we have distributions for all the samples that we consider in this search. So let me try to explain what we have in this histogram, which is actually the distribution that we feed into Pyhf. So here in green, we have the backgrounds coming from cosmic ray interactions, and in blue and light blue, we have neutrino interactions that are background to this search that might happen inside the cryostat and outside the cryostat. You can see that outside the cryostat is a really tiny contribution, but we also consider them. And obviously, we have the data, and we have the distribution for the expected signal in red. Another thing that I want to mention here is in MicroBooNE, we have many, like 5 data taking periods. And for this particular work, we are using what we call run 1. And this histogram shown here is in particular for run 3. But we also feed run 1 as separated channel into a Pyhf. So that's it for heavy neutral leptons. Let me now try to briefly explain the light dark matter search that we are working on. So dark matter models with masses below the mass range are becoming attractive because they offer a rich phenomenology that we can explore, for instance, in experiments outside the LHC. And they might also explain the observed dark matter abundance under certain circumstances. And in order to explain the dark matter abundance, they need to include a new force carrier or more dark matter species. One of the minimal models that we can consider is to extend the standard model by including one dark matter fermion or a scalar, and also a massive force mediator that we call dark photon. And this is the Lagrangian of this model. In particular, in this search in MicroBooNE, we are focusing in this mass regime where the dark photon cannot decay into dark matter particles. It can only decay into a standard model leptons, charged leptons. So the dark trident interaction is a proposed channel to actually probe this live dark matter model. And let me explain what we want to do here in MicroBooNE. So this dark matter candidate can be produced, for instance, in the decay of neutral mesons, such as Pyhf or IRIS, through the diagram that you can see here. Basically, we have the Pyhf, it decays into a photon, an off-shell dark photon, and the off-shell dark photon decays into a pair of dark matter particles. Some of the dark matter particles can reach the MicroBooNE detector, and they can interact with an argon nucleus through the dark trident interactions that you can see here. This is the Feynman diagram of the dark trident interaction. And in this interaction, through the scattering, the dark matter particle radiates a non-shell dark photon that subsequently decays into an electron-positron pair. So as you might imagine, the signal that we can actually detect in MicroBooNE is the electron-positron pair. And this is called the dark trident because of the dark matter and the E plus and minus in the final state. So in a similar way to how I explained the HNLs, let me now explain you how we're planning to search for these dark trident signals. Instead of looking into the absorber here, we look at neutral mesons that are produced by the proton hitting the NUMI target. And here there is an important part of the NUMI beam length, which are the horns. We have some magnetic horns that allow us to focus charge mesons in order to focus the resulting neutrino beam. But obviously, neutral mesons are not affected by these horns. So the dark matter will be produced mostly near the target because the neutral mesons decay very fast compared to the charged pions or charged kaons. So the dark matter particles produced here will travel to the MicroBooNE detector, and they might interact through the dark trident interaction. And this is how a dark trident interaction might look like in the MicroBooNE detector. One nice feature here is as well is that the showers that are produced by the electron-positron pair also points back to the NUMI target in this case. So this is also a nice feature that we can use to reduce any neutrino background. So instead of using VDTs here, we decided to exploit the really nice 2D beam displays that we can make with MicroBooNE, and we trained a neural network, a convolutional neural network, to discriminate signal from background. And the basic idea is that we feed the neural network built in PyTorch with 2D images of signal and background interactions, and we ask the neural network to tell me, okay, is this a signal or a background, and with what score? That's the basic concept. So in a similar way to HNLs, the end product of the full analysis chain are these distributions, which are basically similar to what I presented before for the HNLs. We have in light blue, the cosmic ray background, and in dark blue and purple, we have the neutrino background. And in red, we also have the expected distribution for the signal. And again, this is what we feed into Pyhf. This is just the histogram for run 3, but we also feed the histogram for run 1. So now let me tell you a little bit more on how we implement this in Pyhf. So the starting point, as I said, are the distributions. And we use the JSON template to set all the distributions by following the tutorial that you presented on Monday. And then we obviously need to incorporate all the uncertainties that we have in MicroBooNE. So we have two methods to evaluate the uncertainties in MicroBooNE. One of them is the resimulating method. And in this method, one effect in the simulation is turned on or off, or one parameter is changed by one standard deviation from its nominal value. So this method involves creating an alternative sample starting from a nominal sample. So at some point in the simulation, we branch out and we resimulate samples. That's what we do. And this is typically the approach that we take for detector modeling uncertainties. So in this figure, you can see in black the distribution of the nominal CNN signal score distribution. And in color, you can see the alternative distribution due to the changes in to different detector effects. So what we do in the end is to have an final estimated uncertainty used to these detector-related uncertainties is to sum all of them in quadrature, and that's what we declared in Pyhf as an uncorrelated shape systematic uncertainty. Then the second method that we use to evaluate our uncertainties is the reweighting method. So this method applies for systematic variations that change the probability by which an event might occur. So in this case, we change multiple parameters in the simulation by simultaneously sampling all these parameters within the arrow uncertainties, and we create alternative models using this. And in order to use this method efficiently, we need to repeat this many times to create an ensemble of different possibilities. So the new distributions that we can create by changing these multiple parameters are obtained by reweighting or nominal sample. So here in red, you can see the nominal distribution for the CNN, and the color scale here represents the density of alternative models that branch out from the nominal distribution. So again, we collapse all these alternative distribution by adding them in quadrature, and we also declare this as an uncorrelated shape systematic in Pyhf. But we have also tried some different things here as well. One example of uncertainties that we treat using this method, as for example, the neutrino flux, which is actually this uncertainty that I'm showing here, the neutrino cross-section uncertainty, and the interactions of secondary particles with the liquid argon as they propagate. So let me grab as an example the HNL search now. We obviously fit all these uncertainties using the JSON format. And in the HNL search, we have this set of uncertainties that you can see here, and I'm summarized also in the plot on the right. Now let me go through each of them. We obviously, the first one, which is the statistical uncertainty, we don't correlate them in any way. There is no reason to apply any correlations here. But for instance, for the detector variations, we could try to correlate the signal, the detector variations, the detector uncertainty from signal with the background samples. I don't know if this is actually feasible with Pyhf. We didn't come out with a way to do this. So this is the question that I want to ask here. If it is possible to actually correlate beam by beam, but between samples, like signal and background samples. I don't know if I'm being like precise enough, but maybe we can discuss about this after I'm done. So, but for the analysis, we didn't apply any correlation, and as you can see, it doesn't have a big impact because in the signal-rich region we are statistically dominated, so and any systematic effect doesn't impact the final result by a lot. Here we also have the uncertainty in the kaons that are produced in the absorber, and we correlate them across the beams and in runs in different channels. And finally, these the uncertainties that we have to have using the reweighting method, which are the neutrino flux, neutrino cross-section, and interactions with the liquid argon. We also try to treat this as histosys modifiers in Pyhf and correlate them, and it had an impact. The results were better because we were obviously providing less nuisance parameters, but it's not by a lot because again, we are statistically dominated in the signal region, and that's the major impact in the end. So using the upper limits method from Pyhf, we calculate 90% CLS upper limits on both models, HNLs and dark tridents, and we repeat the same process for all the mass points. And this is where comes to discussion what I mentioned yesterday. for some of these mass points, you expect like crazy and a crazy amount of events. So you're seeing on the strength might need to go above 10, but we can deal here by setting the right matrix element scaling or the setting the right coupling scaling in the dark trident search. So in the end, was not an issue at all. So this is nice. We have here the results for the HNL search in the E+E- channel, and one of the results of the dark trident search for a specific combination of parameters in the light dark matter model. We also did a comparison with one of the frameworks that I mentioned before, because it has been used before in MicroBooNE, which is called Coli. And Coli is a C++/root basic package, which was built within the DCR collaboration, so it's really ancient, and it's no longer maintained. And the goal of this package is similar to Pyhf, to basically provide a framework for statistical modeling and to perform inference, but it has some difference with Pyhf, and since it is older, it only relies on the negative of likelihood ratio, which is just T mu. You cannot change this, and it's only toy-based, because I think by the moment when Coli was developed, the asymptotic formulas were not did not exist. So yeah. The results we obtained from Coli are comparable with the ones we obtained with Pyhf, like 10%, which is very noticeable in the log plot, but which is the final result of the whole searches. So yeah, we are trying to encourage people to move on to Pyhf because it's more up to date and is well maintained compared to Coli, which is not up to maintained. We also tried the toy-based calculation using Pyhf, and in both analyses we did this just for one mass point. And basically, we created the toy distributions and we integrated them, and we obtained results similar to the ones expected with the asymptotic formula, which are within 5%. So also here, I want to ask to the Pyhf developers here. I don't know if there is a quick Pyhf way to plot the respective asymptotic formulas in this case. It would be nice to have like the asymptotic formulas for the
like overlay.
Yeah.
It's just a chi-square, no? Like,
yeah. So I mean, we don't provide like functionality, but as Alex said, like so in the asymptotic regime, it's a chi-square distribution.
Yeah.
Or half chi.
But yeah, it's just that we were wondering with my colleague who worked on the HNL search, it will be great, but it's not a big deal. It's just a question. So yeah, that brings me to the conclusions. Pyhf has been used in recent BSM searches in MicroBooNE. This is exciting, but because we recently published a new HNL search, which is now accepted by PRL. This is the exclusion limits that we set, and you can see that in this region we are actually the most competitive limits here. It's the first MicroBooNE analysis using Pyhf, and the dark trident search, the search for light dark matter, also uses Pyhf, and hopefully will be public in the next coming weeks. So just to wrap up, some things that we love from Pyhf in MicroBooNE is the good synergy with other Python packages like XGBoost and PyTorch, and the flexibility to construct models and store them. And it also because allows difference, uncertainty, correlation, and test statistics that we can perform for that we can use for different measurements. So yeah, that's everything. Thank you for listening.
Yeah, thank you very much for the presentation. That was great. So let's first, we have time for questions. So let's first go to Zoom to see if we have any there. Oh, I see. Okay, we have one from Don Juan. So please go ahead.
Hi, thank you so much for the nice talk. I just have a maybe very naive question on like the geometric setup of the detector. If you go to page 14, if I remember correctly, there was like the observer with the 120 degree with respect to MicroBooNE. And I was wondering how you actually, is this like a optimal, I guess this is the optimal angle to detect this kind of decay processes. And I was wondering like, how do you decide on this angle?
So yeah, that's a good question. I'm not sure if this is like the optimal angle, the one shown here. But I guess there they select or we select this optimal angle by just using the simulation that we obtained from the gains that decay in the absorber. And we see, we should be able to see the distribution, the spread of the angles of the HNLs that will reach the MicroBooNE detector.
Okay, I see. Okay. Thank you.
Okay, so maybe we can go to Jordan next for
Well, I'll
questions.
just bring the discussion I'm having with Alex more publicly. Can you go back to the slide that you were talking about the schematics and sort of the correlations?
Yes.
Yeah, so I guess for this first part here, actually, let's start with the last one where you were talking about the Trinity flux. So, what do you mean that you also tried these synthesis to correlate them? Yeah, you weren't able to correlate them correctly, or you were trying to do.
So the thing is, these three uncertainties, we expect them because of previous analysis in MicroBooNE to be correlated between runs, between channels. So what we tried is to correlate, giving them a hysteresis modifier in the JSON declaration to correlate them between runs. And we noticed that the difference was not like super important in the final result. But for, I mean, this is the particular case of this HNL search because
you're saying that it's a subdominant correlation.
Yes, yes.
So you didn't have an issue actually correlating.
Yeah. No, we don't have an issue. The other thing that I wanted to discuss is this one here. So I will try my best to explain what we would like to do here, which might be useful for future MicroBooNE analysis. So we would like to correlate one beam from the signal sample with one beam with the background sample at the same time that on each sample themselves the beams are uncorrelated.
You want to correlate them between bins of a sample, but not between bins of the same sample.
Yes.
Right. We do have the shape systematic modifier there, which is an uncorrelated bin-wise shape systematic. You basically want to have, I guess you try to do a second shape sys and give it the same name to correlate the shape systematic using parameters, because that's what you try to do, and then it crashes, saying you can't.
Yeah, exactly.
So then I guess then we'll have to open this up because I'm gonna need Mal to use our brain here to explain, because this is an implementation detail I put in Pyhf where we have some modifiers that could be shared or correlated and some that couldn't. In this case, only shape sys was the only one that we just made not shared, meaning we could not correlate shape sys between samples at all. But Alex points out that he can't think of a good reason why that's the case.
Yeah, I mean, I think I'd have to go back and look at when this was implemented to see what the reason was, but
I think, I mean, conceptually, the difference to stat error here is stat error combines effectively aux data from different samples. So like the stat error term, which is correlated across different samples, will be built by combining from all samples the actual statistical uncertainty, summing everything up, and then all samples together vary by the variation that is essentially a function of all the samples individually. So you have a single stat error auxiliary data term per bin. For shapesys, you would not necessarily combine that information, I guess. So you would need to now have multiple auxiliary data points left to keep track of per bin, which I think doesn't necessarily fit into how Pyhf influences at the moment. But that's an implementation detail, right? Again, it's not conceptually an issue, because equivalently, what you could do, instead of having a channel with multiple bins, you just split that up into many channels where each channel is exactly one bin, right?
Yeah.
And then you can use something like a hysteresis, which is now only operating on that single bin, and reproduce that kind of behavior. Of course, it's like ugly now for plotting. Apart across the but conceptually, I think I don't see why this wouldn't be like fine to be used mathematically or like conceptually. I don't see the problem.
Yeah, I mean that procedure that you mentioned, I know that it might be like it's not the cleanest way to do it, but that's something that we can try with my colleagues in Manchester and quantify the effect that we are looking for.
Yeah.
So
Yeah.
maybe with the, for instance, with the dark trident samples, because the means that we have in the final distribution are like 5, so it shouldn't be like super complicated to build the JSON template for that. So yeah, that's a workaround.
Yeah, though we can, I mean, if you put this on the like shared Google Doc and kind of like give some context, then we can definitely, okay, great. Yeah, we can definitely revisit this. Yeah, because as Alex said, this is really just an implementation detail, so we could try and improve on this.
I just thought in the doc as a common problem.
Okay. Okay, we have maybe time for one more question if it's quick. Yeah, so I guess maybe the one question I had is so at like the end you were mentioning that you've been doing these analyses. Does the MicroBooNE collaboration, have they thought about publishing any of the statistical models that have been used for these analyses?
No, there is no like protocol for that or
Okay.
discussion, but I can bring it up in the collaboration meeting. They
Yeah.
might be interested.
Yeah, I mean, I think it'd be like certainly novel, and so I think it'd be interesting to see in general. So
okay, yeah, I will bring it up.
okay, fantastic.